let's give this a shot. Cool. Okay, so last class on we had a look at the transformation stuff. It was all about the application of transformations to a function, having already known what the sequence was. Now we're doing the opposite. Right, now we're trying to look at the functions that we have and try to figure out what sequence would take us from one to another. One of the challenges with this particular topic is that it's one of the few instances where there are multiple correct answers. This is because there are more than one way to get from one spot to another. Right, like if I wanted to move up one and right one, I could also do right one, then up one. The order in which you do things can sometimes be different, so the transformation sequences that you create may or may not be the same as what you see in the book. So there's a couple of ways you can do this as well, beyond just getting different answers. You can use the point type notation that we were having a look at in a lot more detail last lesson, or you could do what's referred to as the transformations by recognition, which is typically a bit faster, but tends to have a bit more room for error unless you're quite used to using it already. Whereas with the point form sort of thing, you can be very detailed with like step by step exactly what you do here, next step, so on and so forth. The other approach is a bit more free form, kind of like how algebra is a bit more free form. There's no like hard rules for it beyond each individual arithmetic thing to follow. So let's have a look at the point form approach. I have all the steps written out. We'll have a look at how they apply to a particular example. In this case, we're going from a transformed truncus to an untransformed truncus. It doesn't really matter where you're starting and where you're going, so long as you identify where you're starting and where you're going. So the only reason I have this specified here is to just give you a bit of a broader understanding of this procedure works more or less no matter what you start with. Example 1 will be transformed to untransformed. Example 2 is the other way around. You'll see quite quickly they are more or less going to be the same thing. So step 1 is literally identifying where do we start and where do we go. This is all about getting our notations correct. So f of x is going to go to the original function, g of x is going to go to the new function. And to get our notation proper, we're going to be rewriting things in terms of xy and x dash y dash. xy is going to go to the original function, f of x, which is why instead of writing f equals all that, we have y equals all of that. And x dash and y dash are going to go to the new function, which is the one you're heading towards, so g of x, which is why we're now rewriting g of x as follows, like that. This gets y dash and x dash into our sequence of equations, which we can then eventually rearrange for. Step 2, get all the transformation factors that are affecting the y to the left-hand side, and all the transformation factors that are affecting the x should therefore now be on the right-hand side. So you're just splitting things up, essentially. So, transformation factors affecting y. We're thinking dilations and translations, some reflections sometimes. Typically it's going to be your dilations and your translations. So in this case we have our dilate of 3 and our translate of 6. Both of those are going to move over just via algebra, right? Subtract 6, divide by 3. A good rule of thumb is to pretty much just shove over as much as possible onto that left-hand side until the right-hand side stops looking like the function it's supposed to be. Like, you could move this 6 and it would still look like a truncus. You could divide this 3 and still look like a truncus. You can't really do much more to this without making it no longer look like a truncus. So we've done it to this stage. You would also do it to this function as well if it had transformation factors, but because it doesn't, there's nothing to be done there. So all that to say, making sure you do it to both functions, not just one function. Any questions about this rearranging bit? I get questions around that occasionally. Cool. Okay. Next up, we're essentially going to equate the x components to each other and the y components to each other. What do I mean by that? I mean, grab the left-hand side of the first equation and equate it to the left-hand side of the second equation. y stuff equals y stuff. Just like that. X stuff equals X stuff. So that one equals that, which does simplify to what we have here. All right, if you just imagine multiplying both sides by their respective denominators and rearranging, you will get to this here. That's the easiest way to think about it. Left hand equals left hand, right hand equals right hand. Fair enough so far. That's also a question I get quite a bit. Sweet. Once you have that, if it's not already the focus of the equation, get your x dashes and y dashes on their own. The reason why is because x dash and y dash, if you remember from earlier, do actually describe the transformation that you're trying to apply. So if we want to figure out what our transformation sequence should be, the thing we care about the most is going to be the x dash and y dash. Due to the nature of the way this one was written, there actually isn't any algebra to be done here. X dash and y dash are already on their own. They're already the subject of their equations. So x dash being x minus 1 and y dash being y take 6 over 3 means that we have this expression. That is our transformation. In some questions, that's enough. Like, this is a mathematical way of saying that this is the transformation right here. But a decent amount of questions want it in a written format instead, rather than like a worded format, sorry, rather than a mathematical expression for it, because they want to make sure you understand what these transformations actually are and in what order they need to be done. Here is where things get ambiguous, because there are multiple ways of doing it. I'm going to present one possible way. So my preference has always been to remove any coefficients from the x and the y if they exist. Right? Like, there's nothing on here, and there's technically nothing on here because the 3 is dividing everything, but we can do a bit of rearranging to make that a bit more obvious. Right? The factor of a third is out the front. The reason I do it this way is because it's more similar to the best practice of when you sketch your graphs. Right? When I take coefficients off of our variables to make sure we're actually revealing what the true translation factors are. So it's a habit that you should already have, and I believe if you continue doing things this way, it'll just further reinforce that habit. If this is the way you go, where you factorize everything first, you're now going to write your transformations in this order. Translation, reflection, dilation. Again, that's if you do it this way, then you do it in this order. I know a decent number of you who have done this topic before in school or such might have heard it the other way around. Do dilate, reflect, then translate. That's because this step that you would have taken previously would be a little bit different, which we'll look at in a bit. But okay, so assuming we take this procedure, translate, reflect, then dilate, all we're going to do is look at each of these individually and then just list them in that order. So for instance, translations, right? We got a translate of 1 left from the x take 1. We got a translate of 6 down from that. No more translate left, no more reflections in there, and our dilation factor is a third. It's either along the y-axis or from the x, depending on what terminology you want to use. One thing worth pointing out is that the x and y are independent of each other. So you can do translate, reflect, dilate on y, then translate, reflect, dilate on x, if you wanted to do it that way. Like for instance, here I've done the 2y transformations, then followed by the x transformation, because they are independent of each other. What happens to the x stays on the x, what happens to the y stays on the y. So as long as you're doing translate, reflect, dilate individually for each x and y, you'll be fine with whatever order you end up doing those in, whether you do x, y, x first then y, y first then x, or if you, for whatever reason, wanted to, you could also intermingle them. If you want to just do like all translates, then all reflects, then all dilates. So all that to say, you're likely to get a fair few different outcomes for this. which may or may not be the same thing that what you see in the answer book, because unfortunately the answers in the book, there's only one of them. I'm pretty sure they don't give multiple correct solutions in there. Any questions about that one so far? We will look at another example briefly. Okay, so when you've got untransformed to transformed, again, you're still following the exact same procedure. The only reason this one is in here is because I wanted to show you that when you get to the stage of doing that whole rearrange for x dash y dash, well, suddenly we actually do have to follow that up. Whereas if you remember previously, it was kind of already rearranged for us. Why is that the case? Well, if the function you're heading towards, g of x, is got the transformation factors on it, then when you do your whole rearranging of things on the left-hand side, like here, we're going to have to minus 3 divided by 2, which gets us to that. When we equate the left-hand sides together and the right-hand sides together, well, the y dash and the x dash have all those factors involved, so you do have to then rearrange for it. Again, if we're following this procedure, factorization is what I'm recommending, so take that coefficient of 2 off of the y. Nothing else needs to be done for the x. Then again, translate, reflect, dilate. So that's going to be your translate 2 right, 3 on 2 up, and then finally your dilate factor of 2. Again, you can see they're written in a slightly different order because x and y are independent. And this one I chose to do all the y stuff first, then all the x, so long as you're following in that particular order. Any questions about that one? Should we try and do an example live together, or do you want to see the other alternative way of going about it first? Is it a different process for DRT? Yes. Different process for DRT is where instead of factorizing, you expand. So basically, if you're trying to be as fast as possible getting through these answers, what you would do is you would look at what your final transformation set looks like. If it's already in its expanded form, then leave it expanded and then do DRT instead. So don't have to take this coefficient of 2 out. If you're doing DRT, you're now going to say dilate 2, translate 3, translate 2, in that order in particular. Whereas if you had it, where is the other one? Had it like this, right, this is already factorized out. I've just made it a bit more obvious that it's factorized out. Then rather than do an individual step of trying to expand it all the way through by doing y over 3 minus 2, then you can just stick with your TRD. So you can intermingle them. You can be proficient in both, and it'll save you a single line of working, more or less. My recommendation is just pick one that you're going to lock in on, make sure it's nice and solid before considering other options. But yeah, if you use the DRT, make sure you just expand whatever you've got. If you're doing TRD, make sure you're factorizing whatever you've got. Is it clear enough, the differences? You do an example with both? Absolutely. Let's do exactly that. Okay. Let's go with this, hyperbola, BI. Head over to the handwritten section. Okay, BI, we're going from y equals 1 over x to the graph of y equals 2 over x plus 3. Okay. From left to right is the order we're trying to do it in. That's going to matter as we follow our procedure. So I'll have the procedure up on the screen share. I'll also have a screen grab of it if you prefer to look at the photos instead. Actually, I'll do I'll do both of these just in case. Saves another screen grab. But you're looking at basically the first procedure here. Alrighty, I'll give you a moment to have a read of what's going on in there and let me know how might we start this one out.
We have to rearrange the original equation, but in this case it's already in the most basic form. Or did we have to arrange the second one?
So we will have to rearrange in both cases. I mean, in this case, obviously nothing has got to do, but this one, there is rearranging to be done, yes. I will say that is step 2, though, where you're rearranging. Step 1 is minor, but important, because we need to get our x dashes and y dashes in there. Otherwise, we'll get a bit confused with what's what. So, original function...
the second equation, same function will have x dashes and y dashes.
That's it. Yeah, exactly right. X dash and y dash goes to the function that we're headed towards. And then, as you said, yep, this one's also going to require a bit of rearranging. What does the rearranging look like for that?
So we can take the 2 to the other side.
Yep. Y dash on 2 equals 1 on x dash plus 3. Anything else?
I don't think we can do anything else.
Yeah, that's exactly right. So that's the only factor that was a y transformation. Again, the other rule of thumb is shove as much over as you can without making this no longer look like a hyperbola, which of course, as soon as we started messing with the denominator, would change the look of the graph or the function. So that's step 2, all sorted, getting everything on our, every y stuff on the y side, all the x stuff on the x side. What else we got?
We have to set the left-hand sides of the equation to each other and the right-hand sides to the equation of the equations to each other.
Exactly right. So red's going to go with red, green's going to go with green. Y equals y dash on 2, and 1 over x equals 1 over x dash plus 3. Nice. That gets us 3a sorted, equating the x's and y's together.
We have to arrange for the x dash and y dash.
Exactly right. This will be fairly trivial. 2y equals our y dash. Cross multiply for x dash plus 3 equals x. X dash equals x minus 3. Cool. This is where things now get into personal preference, how we want to now fully express what we have. So which one do you want to try first? Do you want to do DRT or the TRD approach?
Can we do the DRT first?
DRT? Cool. So for DRT, we just have to make sure that the equations that we have are fully expanded. Now, in this case, there really isn't anything else to be done, even if we had to like factorize or expand it. So things, oddly enough, will end up being kind of the same either way around. Maybe we'll see another example. I'll find another example where they'll be different. But the validation step is going to be making sure things are expanded. So hypothetically speaking, I'm just going to put this plus 1 in there. All right. Let's just pretend that was there to begin with. This would now be in its fully expanded form, so we can clearly now do our DRT in that order. So dilate is going to be what?
Dilations. Do you dilation of 2 from the x-axis?
From x, yeah. It's on the y, so it's in the y direction, or from the x. That's it. For the sake of it, let's also put a 3 here. So we've got another dilation going on there. what's that dilation going to be?
3 from the y-axis.
3 from y. Perfect. Got our dilates going. Reflections. Are there any? How do we know?
There are no reflections.
No reflections.
Both of them positive. The x and y is both are positive.
That's it. Those coefficients are positive rather than negative, so no reflections. All that's left is the translates then, which, well, you can do in any order. Let's just make sure we get them in the right direction.
There's a vertical translation of 1.
Yep, vertical translation 1.
1 unit up.
Yep, 1 unit up.
And 3 units left.
3 units left, exactly. Nice. Because yeah, since we've done it in the expanded form, we've done our D's, R's, and then T's, finally. Now, if we instead do a factorized approach, we're going to do TRD in that order instead. So y dash is now going to get 2 bracket y plus a half. We're taking the factor of 2 out. And x dash is going to be 3 bracket x take 1. So again, taking that common factor of 3 out of both of those. This is TRD. This is DRT. So now when we think about our translates first, we can see they're different numbers. All right, we got a half and we got 1. So we do our 2 translates first. That's going to be half up. It's going to be left 1. No reflections as before. Dilates are again the same number, same numbers as before. So yeah, again we got that dilate 2 from x, dilate 3 from y. So you can see how it's not just that you can do it in any order, it's more so that the way you've arranged your equation will change the individual numbers so that a different order is possible. So the translations have decreased by their dilation factors because you're doing the dilates afterwards. If you're doing the dilates first, you don't need to shift forward as much. Whereas if you do them later, you need to shift forward. You know, you're basically just sort of compensating for different different sequences there. So these are the same thing. I think the textbook defaults to DRT for the most part. That's what I've typically seen. So at least the Cambridge textbook. I'm not too sure about the Jacaranda one. So probably best, at least as far as textbook stuff is concerned, keep it in their expanded forms like this. For TRD, like, all of this stuff is valid. I just sort of think that it's good to have another excuse to practice good, just good principles when it comes to your functions and relations, sketching stuff. Doing good, and factorization is also pretty common for all your other solves as well, like polynomials, you're doing factorization for heaps. How can we tell whether it's horizontal or vertical? That's going to depend on if it's on the y side or the x side. So because this is the y dash equation, everything in there is y related. So in other words, it's going to be your vertical related stuff. Whereas your x dash equation, any of the plus or minuses on the x equation is going to be your horizontal stuff, because x-axis is for the horizontal related stuff. No, all good. It's a good question. This is the stuff that's the most confusing by far, which is why I've had to do. In fact, this is probably one of the first documents I wrote when I started tutoring, because I was like, even in school myself, like transformations was a really tough subject. I didn't know any of this point form stuff. So I was pretty much doing transformations by recognition, which will be the next thing we have a look at. And I was getting mixed results with it because I didn't fully understand. It's not quite, it's a little bit stranger algebra. I'll rephrase that. When we look at this next procedure, it's not quite the algebra that you're used to. It's more substituting into functions. But anyway, we'll get to that in a moment. For now, are we cool enough with this way of doing things? Do we need another example of this to lock it in a bit further, or should we move on to another approach? Moving on. Another example. Yeah, we'll do another example. Cool. So let's do, what's one that's got a bit more in it? We'll do this, this 2a, truncus. Okay, so it's going to be, we're starting at y equals 5 on x minus 3 all squared, and we're heading, wait, hang on, is there more? There's a minus 7 in there. Minus 7, and we're heading towards just y equals, let's try to put that equal sign in there, y equals 1 over x squared. Cool. We know where we're starting and where we're going. That just means step 1 is more or less done for us. We just need to write things out the right way. So which function is going to get our x dash and y dash? Want to give this one a shot, Haley? First one. So the x dash and y dash is going to go to the function that we are trying to transform into. So if we read the question again from the Cambridge book, it says going from the transformed function to the untransformed one. So it's not necessarily that you put x dash y dash on the thing that has transformations. It's more about putting x dash and y dash on the thing that you're heading towards. So if we're going towards this one, then it's this one that's going to get our x dash and y dash. Is that a bit clearer? Cool. Okay. Next step, rearranging the transformation factors affecting the y to the left-hand side and x to the, well, it'll just stay where it was. So we're going to do a bit of rearranging. Obviously this one has nothing to rearrange, it's just a basic function. This one's got some stuff that we could rearrange. Any ideas what we would start moving over? Again, a good rule of thumb is going to be move over as much as possible before the function stops looking like, in this case, a truncus. Yeah, so the 7 is going to be moved over, absolutely, because that's one of the vertical components, so y plus 7. That's it. There's one more that we could move over as well. Divided by 5. Perfect, yeah. We've now hit the translation and dilation factors. And what we can see is at this stage, there's pretty much nothing else that could be moved over. Otherwise, it would break the truncus. This is just a horizontal translation of 3. Cool. That is step 2 done. Step 3 is getting the x's with each other and the y's with each other, or in other words, the left-hand sides of the equations together and the right-hand sides of the equations together. That one's going to be a bit to try and type out, so maybe I'll just do that one quickly. So basically, red pairs with red, green pairs with green. Left-hand sides equal each other, right-hand sides equal each other. Y dash equals y plus 7 on 5, and 1 over x dash squared is equal to 1 over x take 3 all squared. Cool. That's part A of it. Part B is to rearrange for x dash and y dash. So we've already got y dash on its own on the left-hand side, but right-hand side, the x dashes are no longer there. This is just a bit of algebra you guys would probably already be quite used to. Let me know if I need to explain any of the steps, but basically we're going to be doing our cross multiplication, so denominators multiplying each other. X take 3 all squared is now equal to x dash squared, and then finally just rooting both sides. X dash equals x take 3. All I've done is reorder, so we've got our x dash on the left and our y dash on the left. A bit nicer to read. Let me know if anything from that needs a bit more explanation. Otherwise, this is where we get into our sequence, where we're either going to do DRT or we're going to go TRD. And it's going to depend on if we want to rearrange things further, basically how we're going to factor or expand what we currently have. So maybe here's a question actually. Based on the scenario that we currently have with this rearranging, anyone can answer, what would be the most efficient? Again, we're only saving a single line of working, but what would be this scenario, technically speaking, what we currently have? Would this be like a TRD approach or a DRT approach? One of them requires fully expanded, the other requires fully factorized. Maybe the first thing to identify is, do we have fully expanded on both of these equations, or do we have fully factorized on both? I'll rewrite y dash a little bit differently to hopefully make it a bit clearer. So dividing by 5 is the same thing as having 1 out of 5. Yeah, TRD. So let me have a look. So TRD was, yes, this would be a TRD thing. You're right, exactly. Because what you identified is this is in its fully factorized state, right? The 1 over 5 or the divide by 5 is kind of like it's factorized. Yeah. So TRD would therefore be the more effective, or at least most immediate solution available to us. When it's fully factorized, you do TRD. So if we're doing TRD, let's take a crack at it. So we've got T, T, and a D. What are our factors? So let's try the translates first. What translate factors do we have? You can give shorthands as well, rather than using a specific language, although in the actual exam or SAC, make sure you use the specific language. Horizontal left by 3, yes, exactly right. X take 3, so the point is being shifted left by 3. So translate left 3. That's good. That's one of the translates. What else? Up by 7, yep, exactly right. Up 7. Again, I'm using the shorthands. If you want to see like the exact wordings of things, I've got them up on like the screen grab as well if you wanted to have a look at that. But that's more so for when you're doing it again in the real thing. Those are both the translate. All that's left is the dilate, which is going to be what factor, and this is where the wording will matter, because from or along have different endings. Dilate factor of a third along the y. Yes. That's just my handwriting saying it looks like a 3. That would be a fifth, but I'm sure you would have said that if my handwriting looked any better. Yeah, along the y is correct. That's it. So along the y, or you could say from the x. So dilate fifth from x or along y. Typically I see from x in a textbook, but both of these are valid. Cool, that's pretty much it. If we wanted to do the DRT approach, we would have it expanded instead. So this y dash would now look like y over 5 plus 7 over 5. And then you're just doing it in this order. You do that d, this t is going to change to 7 on 5, and well, that t is just going to stay as was. So it depends on, again, if you're expanding or factorizing. Cool. There's plenty to practice on those. The notes have 2 key examples that you can have a look at to reference. So hopefully that should be enough when you're doing your transformation stuff in here. And yeah, also like feel free to let me know if the textbook is giving you different answers, because textbook may be correct and you may also be correct. So it's one of those things where you kind of need a second opinion to get a good idea. But cool. Okay, so we've looked at the point approach for it. Very rigorous, very step by step. It's also a bit long, right? You can see there's multiple steps to it, and although it is very repeatable over and over again, you'll never get it wrong. There's faster ways of doing things, but you just need to be a bit more aware of the nuances around how you do it, because it's a bit more freeform. So I can't really give you a step-by-step procedure, even though that's what this looks like. It's more so guidelines as to how we can be better at doing this stuff. So the question is still the same. Figure out how to get from here to here. Now, in simple examples like this, because there's nothing really going on there, it would be a bit stupid of us to do a full procedure to try and figure out, okay, literally the only difference here is a shift right by 2. So just say a shift right by 2. Going from here to here, that's the only difference. These guidelines are also helpful for when you have a whole bunch of transformations in there that you have to try and work with. So first little guideline is just make sure that both functions are in their general form. And what I mean by that is the form which is easiest to see what each of the transformations are. Like for the quadratic, it's going to be the turning point form, not the polynomial form. Polynomial form, God knows what's going on there. The turning point form, you can see it's a shift right by 2, shift up by 7, dilate 3. You can see all those things. So if we are trying to go from one to another, and this is also true of the previous procedure as well, right? Get this into its general form, which of course for quadratics means completing the square. That's all that is. Next guideline. Again, y transformations are independent to x transformations. So anything you do that's y related is pretty much going to only impact the y. Anything you do to the x is pretty much only going to impact the x spot. Next guideline, typically you're going to want to do things in order of dilate, reflect, translate. This is because whenever you put multiplications onto things, any translate terms that also exist in there are going to be impacted as well. So if you do your dilates first and then put your translates in later, you don't have to think ahead of time what the impact of your dilations are going to be, because you've already handled them. So let's see an example of how this actually works. We're trying to go from here to here. So we can see the dilation factors have changed, as well as the 2 translate factors. We're going from -2 to -1. We're going from +7 to +12. if we're doing things in the order I'm suggesting, starting with dilations, what we need to do is basically figure out what dilation do I have to, or what multiplication do I have to apply to this function to fix this dilate to make it look like this dilate. So going from 3 to 4, the way you change dilates is with multiplication. So you've got to figure out what number do I multiply f of x to make the 3 look like the 4 of g of x. Simple answer, just take this number and make it the numerator. Sorry. Take this number, make it the denominator. Denominators will cancel out because of the current multiplication of 3, and you'll be left with 4. Nice and easy. Multiplying f by 4 over 3 will in fact leave a 4 in that spot. But remember, you're multiplying the entire f. You're not just multiplying that front bit. That's why I put these brackets around here. So as we can see, multiplying by 4 over 3 has impacted that 7. It's now 28 over 3, which is a nice and shit number we don't want to have. This is again why I'm suggesting don't do translation stuff first, because anytime you put in a dilation, you're going to have to then fix it back up again afterwards. But okay, so we've now fixed up the dilations. We can see f has a dilate of 4, g has a dilate of 4. Now we're going to move on to reflections, because those can also be thought of as kind of like dilations. They're multiplying by a negative number. Multiplication is kind of something that needs to be done ahead of time, so we'll look for that. But as we can see, looking at both f and g, there are no reflections in there. So we're happy to skip that over. Lastly is the translations. We can do these in whatever order we want to now. So what have I done first? I fixed up the vertical translations first. I want to go from 28 over 3 to 12. So I just figure out what's the difference between them and then make sure I'm adding that as my result. So adding 8 over 3 will get us to that plus 12 there. Then I need to figure out how to get from x minus 2 to x minus 1. All I would have to do is introduce a plus 1 translation, which feels very strange to do by just shoving a plus 1 into there. It's not quite algebra, but it is substitution. So you gotta basically start thinking in terms of substitutions rather than just pure algebra when it comes to this sort of thing. But again, ultimately we looked at this, we wanted to make it that. The difference between these is positive 1, so we're going to introduce a positive 1 in there. All we do then is write down the list of what we just did in the order that we did it. So we had our dilate factor of 4/3 along the y, or from the x. Then we added that 8 over 3 for the positive y direction. And then we did our translate of 1 in the negative x direction, because when you put plus in function notation, that does go left. Bit more freeform, so it's more so guidelines than anything else on how we can handle it. Before we do one live together, is there any questions about how that's worked? Cool. Let's try and do one together then. So we'll take it a step back in complexity just so we can get one going. Well, maybe not that far back. Something like D. Yeah, something like D makes sense to me. Okay, so we're going from the graph of y equals 2 root 4 minus x to the graph of y equals root x. So we want to do a sequence of manipulations on this to make it look like that. We're going to try and apply them in DRT order, because that'll be the nicest way to not sort of erase the things you've currently done. So for thinking of dilations, we need to figure out what multiplication do I have to put on this function so that the dilate of 2 now becomes a dilate of 1. What factor is going to achieve that? Or in other words, what number would I multiply that first function to turn that 2 into a 1?
Half.
Half, absolutely. So basically, what we're doing is applying a half onto f of x, which is going to turn our function into y equals square root 4 minus x. Cool. I will actually rearrange this ever so slightly, just so we can at least have the x in that leading spot. Okay, there's no more dilations to apply. Now we've got to look for reflections. If there are any, we got to figure out how to, how to change them. There is one. You can see there's a negative sign on the x. This is where the algebra is going to get a bit weirder, maybe. What operation do I have to do to turn this reflection into an absence of a reflection?
F of negative x.
Yeah, so we're going to apply negative x to it. That's right. Now, what is that actually going to look like?
Square root of negative x. So a positive x.
Negative x, like this?
Yep.
Almost. So, is that going to be... Yeah, actually, hang on. So it's going to end up being half bracket f of negative x replaced... Yeah, no, sorry, you're right. This is why I need to write these things out, because even this sometimes confuses myself. Because the operation that you're doing is replacing every x with negative x. So there was a negative x there. You're replacing x with negative x, square root x plus 4. That's the operation. Cool, yeah, sorry for the confusion there. You had it good. So what I'm doing basically is I'm writing the notation of what we're substituting in each stage. It's a substitution rather than an algebra introducing. Anyway, last up, we've got a translate of 4 and a translate of 0.
So half of f of negative x minus 4.
Half f negative x minus 4. That's it. Because now that's going to now look like square root x gets replaced with x minus 4, and there was already a plus 4 there. So y equals root x. They are now a match. And so all we're going to do is write down exactly what we did. We did a dilate of a half. We then did a reflect. I'll leave that one ambiguous for now. We'll get to that. And then we did a translate of some sort. So this dilate here, what are we going to call that dilate? A half from or along what?
There's going to be a reflection on the y-axis.
Yeah, so the reflection part would be about the y, yeah? So about the y-axis. I was asking about the dilation, though. Oh. So this dilate of a half, which one's that going to be? From or along what?
From the x-axis.
From x,
along the y.
Exactly. From x or along y. Perfect. Reflection was done because the negative sign was on the x, so it's flipping about the y. And then lastly, what was the last thing we did?
Translation of 4 units left.
4 units left, yeah. F of x minus 4 means we're shifting left by 4. Wait, hang on. Right. Because now it's in f of x notation. It was already left 4, so to bring it back to baseline, it's now right 4. So, because it's in the f of x notation, x take a thing, that'll be right 4.
Okay, got it. It's because we have to factor it out inside the f of x thing to get the thing.
Yeah, because yeah. So why is that? Because if we take that out, negative bracket x plus 4 probably just means that I've been doing this notation a bit loosely. because as written, if I just do that notation into this, I'm pretty sure it's not going to work quite well. I was kind of just adding the numbers in as we wrote them, because if we look at what that would be, half, I guess we'll find out real quick. So y equals, so it'll be a half times 2, then root 4 minus, so every x is getting replaced with negative bracket x plus 4, bracket negative bracket x plus 4, all rooted. Y equals root minus minus makes plus. Oh, sorry, there was already a thing there. 4 plus x plus 4. So yeah, like the notation as I wrote it isn't quite right, but that doesn't change from the fact that like doing it in that order was good. It's just that I was writing it incorrectly on here. It is still what we did, half from x, then we did a reflection, and then we did our shift. When you put the plus 4, that would be, no, sorry, we did a minus 4. What am I saying? We introduced a minus 4 into it. So more so think about what you've introduced rather than this. If I were to write this out properly, each of these would kind of get their own new function. Like half f of x becomes g. Then we would have g of negative x is our new, I don't know, u. And then finally it was u minus 4. So u bracket x minus 4, because you're changing the function at each stage and you're introducing it into the new function. So I apologize for the weirdness of what this looks like. Think more so, what did I do at this stage? What did I do at this stage? What did I do at this stage? And then do it in that order. Is that a bit clearer? Probably shouldn't have had these in there. Should have just said, this is what that one is, this is what that one is, this is what that one is. Cool, cool. So, as we can see, it's a bit more complicated. I'll also tend to have a few trouble with it here and there. But it is faster. We've got all of our working out on the same page versus... maybe it's closer. Yeah, it's kind of similar, actually. The amount of work that you're doing. This is just a question header, so is that. So that's the same amount of space. Rearranging. This could actually be done even shorter if you do both your rearranging in the same step. And then, yeah, I guess they are kind of similar levels of complexity because you're doing algebra at each of these stages anyway. But yeah, I mean, both of these do work. It's just up to which one you prefer, really. Cool. We've got time for one more that we can have a look at. What procedure should we want to use? You got the, where is it? Point form or recognition. What we just did was recognition. What we were doing previously was the point form. No preferences? Cool. We'll do a point form one then. Let's see, what's a decent one that we could do? Let's do it where they've got both transformations, actually. Yeah, we'll do these roots. So y equals 2 root 2 minus x plus 3, and we're going to y equals negative 5 root x plus 6. Cool. Going from top to bottom. with that in mind, let's take a stab at it. How are we going to start this one off? Step 1, identify what's the original, what's the new function. This is where we're getting our x dashes and y dashes in the right spots. So which of these functions is going to get our x dash and y dash?
The second function will get x dashes and y dashes.
That's it. Yep. Nice and easy to just plug those dashes in there. Sweet. Step 2, get the y stuff on the y side, the x stuff on the x side. Now we've got two functions to do it with. Well, we always have two functions to do it with, but sometimes one of them doesn't have anything to rearrange. Let's start with this top one. What's the rearranging going to be for our y and x?
We take a 3 and the 2 to the other side.
That's it.
So y minus 3 over 2.
Yep. That's good. How about the second one?
The second one, we take the 6 and the 5 to the other side, so y minus 6 over 5.
Y minus 6 over 5.
Negative 5.
Yeah, okay, negative 5, cool.
Yeah.
Negative 5, and that's just going to have root x left over. Yeah.
We can take the negative up top.
We can, yep. You can have it either factored in or expanded through. That's more of a personal preference thing. Once we have that, so that's going to be our step 2 all done. Step 3. What's going on there?
We set the left-hand sides and the right-hand sides with each other.
Yep. So it's going to get us y minus 3 on 2 is the same as minus bracket y dash take 6 over 5. And we're also going to have root 2 minus x is equal to root x. Where hang on, x dash. Forget how that's going in there. Cool. Which variable do we need to rearrange for? The dashes or the non-dashes?
The dashes.
Dashes. That's it. This shouldn't be too bad. Cross multiply. 5 bracket y take 3 equals negative 2 bracket y dash take 6. Okay, so divide everything by negative 2 and add 6. So 5, negative 2, y take 3, and then the plus 6 is going to go out there. 5y minus 15 over negative 2 is our y dash. And again, square both sides. 2 minus x equals x dash. So let's just bring it down here. X dash equals 2 minus x. Just for the sake of good convention, we can bring this negative back up. So that's going to get us 15. Actually, let's keep them in that order. Minus 5y plus 15 over 2. Cool. We have our x dashes and y dashes. Next is going to be to figure out, are we going to do a TRD, are we going to do a DRT? It could depend on what you're given, but it also could depend on just whatever you're more comfortable with. What are we thinking?
We can do TRD.
We can do a TRD, yeah. That'll be the most immediately available because this is in its factorized state, which I'll probably go, just for my own sake, make it more obvious what's what. Cool, so if we're doing TR and D, we got a couple of translates going on. Maybe I'll, again rewrite this so that's a bit clearer. Having the X on the, that's just basic convention. All right, we got a couple of translates. You got a reflect, 2 reflects actually, and a dilate. What are we looking for? Translates.
Translation of 15 units up.
Yep, 15 up because it's on the Y thing.
And then a translation of 2 units right.
2 units right. Yep. Got a couple of reflects going on. So, I mean, it's kind of hard.
Reflection of both axes.
Exactly. Yeah, reflection of both. You really can't get this wrong because you can do them in any order. So, yeah, reflection X, reflection Y, or other way around, same thing. And then our dilate. What's that going to be?
Dilation of by a factor of half on along the x-axis.
Along or from?
It's
The dilate half.
from the y-axis.
So
Wait,
you want to
no.
go ahead.
Wait. Could you give me a second? I'll just
Yeah.
try and
Yeah, take your
understand it.
time. So the dilate factor of a half is in your y dash equation.
From the x-axis?
From x, yeah. So if it's on the y equation, it's going in the y direction. So you either say it's along the y because that is going in the y direction, or you say from x because let's just quickly remind ourselves. This direction could be seen as going along y or away from the x. They mean the same thing. Cool. That'll be about it then. A nice big chunky one there to finish it up. If there's anything further to clarify, feel free to let me know. Otherwise, I'll let you enjoy the rest of your day. Thank you.
Thanks. Have a good day.
Thanks. You too.